Hey, what's up YouTube? So here we are. We are on day 8. Let me see here. The first 7 days we covered model 0, the linear model, and now we're going to move on to something more fancy, quadratic relationship. So this model assumes the nonlinear relationship as the zone temperature and set point grows. So like when the building sits off all night, HVAC is not running, the temperature and the zone temperatures and drift. Hotter in the summer and colder in the winter. So that's our delta T, is the difference between the zone temp and the occupied temperature set points. So this is supposed to mimic more of like the real world physics, because this like constant rate, degree per minute models that apparently, like if you would study the theory, if you had a degree in mechanical engineering, which I do not, that you would actually study like the physics a little bit more in depth. Okay, so this is we're going to look into more better relationship quadratic model, and they're calling it medium hard. Requires basic algebra, and we're actually doing this in the Niagara program object on the vibe coder, the quadratic model. We're only doing these ones and model 1 because you don't need any fancy math libraries to do the quadratic model. Any coding language can handle that. Okay, so kind of done with this one. Model 1, manual simple regression. So in this formula, the duration T is dependent, that's our minutes, our prediction minutes, is the dependent variable Y, and the squared temperature difference. So they're squaring that zone temperature and set point, is the single independent variable. The implementation model 1 implements the core tuning logic by manually calculating the sums, ordinary least squares. That's regression. Simple linear regression has basic closed forms that are short and reliable, blah, 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 blah. Okay, so they're saying this is just like a really fancy way of doing linear regression. It looks kind of confusing, but I think that we'll get into calculating like the slope of a line in this week. This was really going to dust off some math skills for me. So there might be a little bit of struggle on my part because I've been out of the calculating anything in math manually for a long time. So yeah, it's just basic math that any coding language can handle, and then we're basically just factoring in squaring that delta temperature. Okay, so let's get into the lessons. Here we go, day 8. Day 8, 42 more to go. So far, so good. Okay, day 8, why heat transfer isn't linear. In our AI created lesson plan, recognize that warm-up time grows faster with delta T. Many buildings, the last few degrees take longer than the first, which is probably true. So like if your zone is really cold, you might get a couple of degrees, right away in the beginning when the air handling unit starts pumping out some heat or a heat pump. But then that last little bit to zone temperature set point might take a little bit longer than the first initial push. So this nonlinear behavior occurs because heat transfer slows as the zone approaches set point. The walls, the furniture, and the air must all warm up. That makes sense. PNNL's model 1 captures this by squaring the temperature difference in the equation. This square term makes the runtime grow rapidly with large delta T, making it match reality. Interesting. Okay, so how to use it. Apply this concept using the formula or algorithm provided. Prefer a mini equation. Understand the concept allows you to build more accurate, efficient, optimal start models, improving comfort and savings. Okay, so here we go. Here's our equation. This, where's our equation? So this is like our equation from the white paper. So it's this parameter A times delta T squared plus B. So this is our delta T, this is our alpha A parameter, minutes per degree squared in minutes. I'll have to sit there and look at this a little bit. So this is our predicted minutes. Okay, let's try it out. Run a little bit of code here. Python. All right, so this is if this was our equation, which we're going to get into a little bit more detailed, and then even use like a historical data structure, that we would see you know, these parameters changing over time. The math equation gets tuned. Okay, so you know, we did that, printed 56 minutes. So using A equals 10 and B equal, or 1 and 3, compute 4 and 8. Okay, so alpha, hold up. So A is 1 and 3. So they're saying to use 1 and 3 down here. So this is then different delta T of 4 and 8. So we could say maybe delta T1. Let's do, actually, you know what we could do is do a data structure. So delta T's, and they said to use 4 and 8 in Python. I don't think we have to get really fancy about declaring if it's a float or an integer. In other coding languages, the coding language would get throw an error if we tried to use a floating point to an integer whole value, but in Python it's kind of nice. It'll handle that all under the hood. So we could just do for delta in delta T's well, maybe we could just change this. Whoops, there we go. Let's try that. So, wow, is that a big difference? So this is, here's our parameters. So that is definitely, would be not linear change right there. So we can even add in a couple more of these just for fun to see what it'll do. Let's try even adding in a float value. So yeah, definitely a non-linear model. So we could even plot these like we did before, and this should actually be like a curved chart. So apparently the like the, you know, this would mimic more of the real world physics rather than just a straight kind of continuous line. You would have more of like a curve to it for calculating minutes. Let's see, let's get back here. So given the example of high minutes, okay, so yeah, we did that. Explain why delta T how that was handled during the curved relationship. Give an example of a high mass zone where Model 1 would outperform Model 0. So I think like if you had a building full of concrete, for example, compared to a building that was maybe stick framed, like the concrete building would have so much thermal mass, I think, that the huge difference in the heat transfer calculations and the physics. So that would be, it could be just a little bit different in the amount of, the characteristics that it would take to warm up that zone, where maybe a linear model of just kind of a simple construction, lightweight, could be more of linear degree per model. I'm kind of guessing at that, but I think that's kind of asking us what it's asking us to try and imagine. But so yeah, I guess that is it for today. So it's almost tempting just to see like if we could blast through maybe 2 of these days. All right, so now we're now we did the same thing that we just did before, where they're just doing DeltaT in the saved data structure. So they're just saying in Model 1, the Intercept A and B accounts for fixed delays. So these would be fixed numbers. The lag in the sensor lag, the lag in the zone's actually warming up. Even if the DeltaT were 0, you would still need a few minutes to circulate water or air before the temperature change is measured. So that's kind of why the paper defines it as a resistive capacitance type of models. All right, so here we go. So the PNNL paper defines A and B as the minutes required to change the indoor temperature by 1 degree. Choosing A and B appropriately prevents the model from predicting 0 runtime when DeltaT is small. So we basically did this. We had like a little data structure where we were kind of added a few more in, and we kind of showed that curved relationship. So explain why the predicted pot is never less than, explain why predicted time is never less than A and B. That's interesting because we're always adding it. So there's no way that it can go less than that. How would you estimate A and B from historical data? Ooh. So this is the process where I think like we would start tuning these numbers in time. So like after we predict, we go back and we retune these. So I'm really curious to get into that. What building components contribute to dead time during warm-up? Yeah, so it's a good question. Like what we talked about above here is a few minutes to circulate water or air before any temperature change is measurable. I know when you tune PID loops, there's like, you do a step test and you always account for a factor of time that you need the sensor to react, and then the unit of time that the sensor value stops reacting. So that's why I'm kind of thinking it as something a little bit like that. There's units of time that it takes by the, you open up that hot water valve, water rushes into the coil, and then there's always like a little bit of lag before you actually see the temperature rise. And like when you actually heat up the walls and floor or whatever the spaces inside of a building, there's going to be lag. Cool. Okay, so we did days 8 and 9 today, so hopefully it shouldn't be too hard. So that's all for today. Let's see you guys tomorrow for day 10.